implementation world, but I'm hoping to, oh, actually I should give the signal for start recording. Yeah. What do we have? Ready for recording when you are. Okay, sounds good. Yeah, so something that is mostly a research project at this point, but I'd like to, extend it to more of a machine learning system in the future. And so I'm going to talk about AI-guided experiments for ML systems, AutoML, and science. This is with a number of collaborators, a couple projects in here from different universities. As background, I'm a postdoc at Stanford, so this is with some of my collaborators at Stanford, as well as with some folks from CMU and some folks from National Lab, so the SLAC Accelerator National Laboratory that we work with. Okay, so experimentation. When I say experimentation, I view this as the process of taking actions to acquire data that's useful or informative for a given task or to estimate a given quantity. So experimentation comes up all over the place in science and engineering, from materials design, drug discovery, robotics or reinforcement learning, for example, exploration or active learning, optimizing computer systems, and more generally AutoML, things like hyperparameter optimization and neural architecture search. A lot of the work in this area involves sort of topics or fields such as active learning from the machine learning community, optimal experimental design from statistics, as well as generally a broad set of Bayesian methods. And the thing that I want to talk about today is a new framework that I've been working on for flexible experimentation, sort of broad purpose experimentation, which extends a classic method called Bayesian optimization from estimating global optima to estimating a broader set of properties that can be used in different experimentation tasks. And later, we aim to incorporate this method into a broad purpose experimentation system down the road. Okay, so, oops, wrong direction. Okay, so let me first give some background on black box global optimization. So suppose that we have a noisy black box function, which we'll call f. You can query f on an input point x from some domain, and you can observe an output y. And we're going to assume that observations are noisy. So the observation y that you observe is a noisy version of f applied to a given x. That each function query is costly, for example, in money, time, human labor, or otherwise to do an evaluation. And the goal of this task is essentially to estimate the location of a global optima of f within a limited budget of queries, let's say within a budget of capital T queries. So there's many different applications of black box global optimization in different areas. A couple of which I mentioned a second ago. So in AutoML, hyperparameter optimization and neural architecture search sort of classically has been framed as a task of black box global optimization. Systems auto-tuning, for example, in databases or web servers, some projects in industry that are using black box optimization for these kinds of tuning tasks. In the sciences, in national labs, there's been a lot of work on optimizing laboratory equipment and machines, such as in the accelerator space or in tokamaks in the plasma fusion world, as well as materials discovery and protocols. So a couple of the figures I have up here is for using these methods for catalyst design or for battery charging protocols to get better performance out of certain batteries based on how you charge them. So a popular method for carrying out black box global optimization is known as Bayesian optimization, or BO. This leverages a probabilistic model of f to sequentially choose a set of queries of the black box function, where this model basically can incorporate prior beliefs about f, for example, its smoothness or maybe other properties, to tell us where we're certain versus uncertain about the value of the function. And you can use this uncertainty for sample efficient optimization to essentially plan out a sequence of queries that are informative for quickly doing black box optimization. But the goal of this project is basically in a number of real world tasks, there's a variety of other properties beyond just global optima of a function that you might want to estimate that are useful for different tasks. So let me just walk through a quick list rather quickly here. So there's first of all different variants of optima that you might want to estimate in addition to a global optima. For example, you might care about a local optima with respect to some initialization point. You might care about the top k optima of a function if you want multiple optima that are, for example, diverse. In multi-objective optimization, we actually care about estimating a property which is a Pareto frontier of a multi-objective landscape rather than a single global optima. In level set estimation, we care about sub-level sets or super-level sets. So this is a subset of your domain whose value under the function is above or below some threshold that you define. In search task, we care about finding a subset of your domain that has value that matches some criteria. Phase identification, you care about estimating boundaries or partitions of a black box function. In some tasks, you might care about estimating roots. Quadrature, you care about estimating integrals, expectations, or averages under a black box function or a density function. You can actually view a black box function defined on graphs. You might care about estimating certain applications, properties of a graph, such as shortest paths. In sensor placement tasks, we care about finding the function value itself at a predefined set of locations. And you can even view certain aspects of reinforcement learning. If you have an unknown environment transition function or dynamics function, you can think of estimating an optimal trajectory or policy as estimating a property of a black box function. I'm going to talk about that more in a second. But the goal of this project is essentially to develop a method to estimate a broad set of function properties within a limited budget using probabilistic models. So you can view this as a generalization of Bayesian optimization to other function properties beyond global optima. So the first question here is, how do we formalize this notion of other function properties? Because it's sort of an abstract thing. So what we do in this project is we're going to define a function property with the use of an algorithm. So let me describe what I mean by that. So note that if you have a function property of interest that you want to estimate of a black box function, there often exists effective algorithms for either computing or numerically approximating this property if you were to ignore the budget constraint. So if you didn't have to do it within a limited set of queries, you just wanted to compute it, it's very cheap, there exists an algorithm that you could define to compute the function property. For example, suppose the property that you care about is a local optima with respect to some initialization point of a black box function f. You could then run some local optimization algorithm. For example, gradient descent, or the Nelder-Mead method, or an evolutionary algorithm. With essentially, I'll have the following strategy. You start at some initialization point that we assume you've pre-selected. You take a sequence of steps, essentially going downhill until you converge at some local optima, some local minimizer, and then you return the best query found so far. So this is some local optimization algorithm that isn't really sample efficient that you could apply to a black box function to compute this local optima property. Or let me give one more example. Suppose you want to compute an integral or an expectation of a black box function. What you could do is essentially apply a numerical integration algorithm, such as a rectangular or trapezoidal approximation, where you basically take the region over which you want to integrate. You can define a grid, and then over the grid, you take a query at every grid point. You compute the black box function value, and then you approximate the integral with a trapezoidal or rectangular approximation. So this is another algorithm that you could apply to a black box function to compute this integral or expectation property. So generally, I'm going to define a computable function property as the output of a given algorithm, we'll call it A, if it were run on our black box function f. So all the previous properties that I mentioned are computable function properties because there exists an algorithm that could return this property as output. Integrals, local optima, level sets, Pareto frontiers, partitions, etc. Because you could define an algorithm that returns this property. And I'm going to define the task of Bayesian algorithm execution, or BAX, as the task of estimating a computable function property, or equivalently estimating the output of this algorithm A, using only a limited budget of T queries to F, even if this algorithm A requires far more than T queries. I should also mention, if we have questions kind of during this talk, yeah, maybe a quick question.
Are there any constraints or requirements for what the algorithm could be? For example, inputs that it takes or the outputs that it produces?
Pretty general purpose. It's got the main thing is it's got to take a sequence of queries on the black box function, we're assuming. Yeah, and it's got to end in a finite amount of time. There's probably some details about the complexity of the algorithm that's important here that I haven't qualified so much. Yeah.
Just to clarify, you said, for example, Pareto frontiers, in this case, it would output a number of points that are inputs to the black box.
Yeah, it would essentially compute that Pareto frontier even in a non-sample efficient way. Yeah, so notice that we're framing a property here that we want to estimate in terms of an algorithm, right? And there's two main reasons to do that. The first thing is that it gives a flexible way to define function properties. You can slightly change the algorithm. You have a slightly different property that you've defined very, very clearly. And second of all, it's actually going to give us the procedure to do the sample efficient estimation, which I'll talk about now. So methods for BAX. I'm going to describe InfoBAX. So-called InfoBAX is what we call it, which is a method for BAX that's based on information theoretic methods for Bayesian optimization. So just as some background, There's information-based methods for Bayesian optimization, which are usually referred to as entropy search family of acquisition functions in Bayesian optimization. I'll describe them in a second. They're all based on Bayesian optimal experimental design, or BOED. And the general idea behind BOED is that suppose that you have a model with an unknown parameter of interest. You basically want to choose a sequence of experiments that most reduce the uncertainty about the parameter at each iteration, where the uncertainty is usually defined as the entropy of the posterior distribution over that parameter. So to describe this InfoBax method, I'm first going to describe information-based Bayesian optimization, then talk about how we extend it to information-based Bayesian algorithm execution. Okay, so first, just visualizing how Bayesian optimization works, and then info-based Bayesian optimization. Suppose that we have a black box function. In this case, it's a black line on the screen, defined over a one-dimensional domain X here. And suppose that we've got 6 queries of this black box function, which are these 6 black X's here. And suppose that we have a probabilistic model that we want to apply for modeling this black box function. So given these 6 queries, we can essentially visualize some probabilistic model over functions, which I'm denoting as these gray bands here. I'm showing posterior samples of the function in these colored lines here on the screen. Based on this posterior model, we can then define what's called an acquisition function. An acquisition function denoted as alpha of x, basically aims to describe the value that you would have from querying at any point in your domain. So this is something that's defined with respect to the Bayesian optimization algorithm, aims to show the benefit of what you get, like the amount of information you get from querying along any point in the domain. So what you do at each iteration in Bayesian optimization is you optimize this acquisition function after defining it to find the next point to query. And then you query this point on the real black box function. So this is the expensive query. You get a new data point, you add this to your data set, and then you iterate. So this is the algorithm I just described here. For a sequence of iterations, you optimize your acquisition function, then you query your black box function here. And the key step is really defining and optimizing this acquisition function to define a given procedure. So for information-based Bayesian optimization, what's the acquisition function? Okay, so going back to this visualization of samples from the posterior distribution over functions, for information-based Bayesian optimization, suppose that we plotted the global optima of every sample here in this pair. And I'm going to plot the global optima as a red dot. So this is the set of global optima associated with each of these posterior samples. You can actually think that there is an induced posterior distribution over global optima that's given by this probabilistic model. So really think of this as a distribution over the location on the x-axis of these red dots. Okay, so this leads us to the acquisition function for these entropy search family of BO methods, which is the following. Let me just parse this equation here. So this is the acquisition function alpha for a given input x. It's defined to be essentially the entropy or the uncertainty of the posterior distribution over these location of these global optima. So the uncertainty over the location of the distribution that you see samples of red dots here, minus the expected uncertainty of the same posterior distribution if we were to make a query at a given input x. So you can really think of this as the expected decrease in uncertainty if we were to query at a given x, the expected decrease in uncertainty over that distribution of red dots there from the previous slide. And this is known as an expected information gain, or EIG acquisition function that's used here. Yeah, so this is for information-based BO, but we're going to use a similar thing for information-based BAX. Recall that the goal is of the BAX method is basically to estimate a computable function property using a limited number of queries to our black box function, or equivalently, you can view this as estimating the output of an algorithm because there's an algorithm associated with each property. So we're going to take a similar BOED strategy here, just for some terminology. Denote the output of the algorithm A as O sub A, and we're going to care about the posterior over this output, which is P of O sub A, given a data set D. This data set D is the set of those X's, those queries that we saw before. And in particular, the entropy of this posterior over outputs of algorithms. And we're going to want to make queries to best reduce the uncertainty over the algorithm output at every step in this procedure. So we can also define an expected information gain acquisition function, which will look quite similar to the previous slide, but just with a couple terms different. So for a given x, this acquisition function is defined to be the uncertainty of the posterior distribution over algorithm outputs minus the expected uncertainty or entropy of posterior distribution over algorithm outputs if we were to make a query at a given input x. So again, this is the expected decrease in entropy of the algorithm output if we were to query the function at a given point. This is again an expected information gain acquisition function. Okay, so how do we compute and optimize this in practice? First, I need to define one more thing, which is called an execution path of a given algorithm. So I'm going to define an execution path as the sequence of queries or the sequence of XY pairs that A would have made. A is the algorithm associated with the function property, if you were to run it on your black box function. So before I describe these algorithms that you don't care about sample efficiency that's associated with a property. So take this local optimization algorithm where you initialize at some point, you go downhill until you find a local optimizer. The set of queries that this algorithm A would have made on the function that you apply it to is the execution path of this algorithm. Okay. So a couple things to, and so the pink dots basically in this slide. A couple things to note, you never know the true execution path because we're not actually going to apply this algorithm to our black box function. What we're gonna do is actually apply this to posterior samples from the black box function. However, because we're assuming here basically that the algorithm would take too many queries. It would be sample inefficient if you applied it directly to the black box function here. What we want to do is design a sequence of queries to estimate the output of this algorithm in a sample efficient way. But what we do have, we can actually consider a posterior distribution over execution paths, and that's going to be used to essentially compute this infobax acquisition function. So let me visualize this acquisition function here. Going back to this visualization before, where we have a posterior distribution over functions, where we have a number of samples drawn as these colored lines. Consider one function sample. Suppose we took our algorithm A and we applied it to this function sample. We would then get an execution path of algorithm A on the sample, which I'm just drawing an arbitrary algorithm here as this sequence of red dots. Okay, so we can actually do this for many samples and get a set of these execution paths. And you can even consider, just as before, there's a posterior distribution over execution paths that's induced by our probabilistic model. So how do we actually use this in practice to carry out the infobax acquisition function? There's two stages here that you can carry out in a pretty computationally efficient way. The first stage is before acquisition optimization, and the second stage is during acquisition optimization. So before acquisition optimization, you essentially take your probabilistic model, you take posterior samples of a function, and you run your algorithm on posterior samples to get a set of samples of execution paths. And you cache these. And then during the acquisition optimization procedure, you essentially can approximate an expected information gain value of a given input X using these cache samples. So it's actually pretty computationally efficient because what you can do is run whatever algorithm you define that specifies a property once at a given iteration of BO on a set of function samples. And then using this, you could quickly do optimization to figure out where's the most informative point to query to get most information about the algorithm output. And this has a similar structure to information-based Bayesian optimization, how they do it in practice to compute the acquisition function there. Okay, so with the last few minutes here before we go into questions, I just want to describe a few applications of BAX that we've been working on in practice. We've actually, so this paper originally was in ICML last year. And since then, we've been really trying to flesh it out to apply it to different applications. We've been working on places in both the sciences primarily, but a little bit of machine learning applications, ML systems. There's been some other groups that have also kind of extended this to some AutoML stuff, which is pretty cool. I just wanted to describe it sort of a high level view. So yeah, the three main applications that I want to talk about. The first one is in what's called emittance tuning in particle accelerators. So particle accelerators are big machines. The one that's associated with Stanford is called from a lab called SLAC National Lab, and they've got like a 2-mile long particle accelerator. And you really care about certain properties of the accelerator to get good performance when you use it downstream in imaging applications and other type of applications to study physical properties of particles. You care about something called emittance. And usually you need to tune, either there's operators who tune it by hand, or they've tried to explore automated tuning procedures for emittance and particle accelerators. But we actually, based on looking at a slightly different optimization setting, are able to reduce the time of automated tuning and get better performance than expert operators Second of all, we've been using this in model-based reinforcement learning. So here we essentially view a property of an unknown dynamics function. You have an environment with an unknown transition function, and you can view the process of estimating optimal trajectories from a given start state or from a distribution of start states as estimating a property of a black box function. We use this for defining optimal exploration in RL. And then finally, in explainable hyperparameter optimization, this is actually by a different group from University of Hanover and University of Munich, tried to do both hyperparameter optimization with Bayesian optimization. But if you don't just want to do optimization, you actually want to estimate some information about the marginal effects of hyperparameters. So get some information that tells you for a single dimension of the hyperparameter space, if you marginalize over the other hyperparameters, so you can see what is the importance of this single hyperparameter if you were to vary it. How do you estimate this quantity while also doing optimization at the same time? And you can define a BAX setting for this task. So just high level slide each of these things. For the particle accelerators, we run it in a setting called multi-point query setting, just based on how each query is set up in these particle accelerators for querying the admittance. You actually do this scan over an alternative space, so you can define a much more sample efficient BAX method rather than Bayesian optimization. We've actually run this live at two different particle accelerators at SLAC. So one's called the LCLS, the other one's called Facet2. We're able to get something like 24% lower admittance than hand tuning by the current operators in practice, as well as something like 20 times faster than Bayesian optimization for automated tuning. Second project I mentioned is, how do we do sort of more optimal exploration in model-based reinforcement learning using this technique? What we do here is we're essentially developing either depending on the RL setting we're working with, we're making a plan to take actions that are expected to gain information about an optimal trajectory from a given point or from a given set of start states. So this enables doing efficient exploration in RL. We've got a couple of papers on this from this year. So one in iClear and one in NeurIPS that basically do this in two different settings of RL. And then finally, this paper by the group from Germany on explainable hyperparameter optimization. They're essentially doing, as I mentioned, simultaneous Bayesian optimization while also estimating these marginal effects. So if you marginalize out other hyperparameters while focusing on individual ones, can you estimate this quantity to essentially give you the importance of individual hyperparameters? Okay, so final slide here. In summary, we extended Bayesian optimization from targeting global optima to targeting other function properties that are defined with an associated algorithm. This is the task of BAX, as we've called it, and we've got a acquisition function based on information theory for this called InfoBAX, and we've been applying it to some applications in science and machine learning. If you want to know more, please check out this BAX website. I think this gives a more sort of intuitive overview and also links to the code and things like this, as well as the paper. And in the future, we're hoping to really kind of make a good systems implementation of this so we can extend this out to a broader set of experimentation tasks. And thank you for listening. Cool. So I guess we've got 1 minute left, so maybe a couple questions, or we should maybe start setup of shifting.
I think it would be best to hold the discussion for the next coffee break that's coming up.
Sounds great.
And we should check if our speaker system is online and ready to be connected.